Many different filter technologies are available for filter design and creation. I'm going to talk to you a little bit today about the different filter technologies we offer and about some of the trade-offs that are involved in selecting the right filter for the job. So, for example, let's just say you had a 100 megahertz bandwidth bandpass filter requirement and you wanted it centered at a frequency of 1 gigahertz. There are a lot of different ways that can be done. That could be an LC filter. It could be a cavity filter, a comb filter. Really any kind of distributed technology would work as well. So the difficulty is in selecting the right set of design trade-offs and design constraints so that you get the optimal filter for the job. And that could involve weight, cost, size, electrical performance. And so I'm going to show you some examples of a few different filters that take these different characteristics into account. This large tubular filter is an example of a filter that has some pretty extreme electrical performance requirements. In this case, the customer required really low insertion loss at cutoff, a really high rejection close to cutoff frequency, and a really wide bandwidth. So fortunately for this customer, size and weight obviously weren't a constraint because the solution was this 39-pole tubular filter that has quite a bit of mass and weight with it, as you can see. Now, on the other end of the spectrum, if the electrical performance requirements could be relaxed, this same filter could be done in a little LC filter, inductors and capacitors in this little drop-in package as an example. Now this filter won't have nearly electrical performance of this, but you can see the advantage in size and weight and cost with this smaller filter. Another example of a filter that has great performance would be this cavity filter. This one operates at 900 megahertz. It's narrow bandwidth. The insertion loss characteristics and the power handling characteristics of this are phenomenal. They're very, very good. Again, a bandpass filter like this could be designed with these same specifications. It's just that it's going to have a higher insertion loss, lower power handling, not quite the same performance. Now, an example of a filter that's kind of in between these two is the ceramic coaxial resonator filter. This filter, again, could be made to operate here at 900 megahertz. The insertion loss of this filter would be somewhere between this one and this smaller one, and the cost as well, somewhere in between. Now, a lot of times, size and weight, or at least weight, is a big concern, especially in airborne or drone applications. So we've developed a ceramic or a cavity filter that uses a tough plastic as its base material instead of aluminum. You can see this one's made out of aluminum, and it's got a fair amount of heft to it, a fair amount of mass. This filter, made out of the durable plastic material, would be much, much later, about the third the weight of this one. This filter shows the final product after it's been plated. This filter, like I say, is about a third the weight of a metal filter of the same size, and it has about equivalent electrical performance. So this is a nice type of technology that can be used in applications where weight is an issue. Another filter that combines lightweight and small size is this ceramic filter. You can see how small that is. This is really ideal for an airborne or lightweight small size application. That filter operates at 20 gigahertz. Now, filters in that frequency range are often either connectorized in a metal housing or they're waveguide based, or they have to use some kind of a special process such as wire bonding in order to be integrated into the end customer system. In this particular case, we worked with the end customer circuit board stack-up to provide a part that is attached using standard soldering practices. So in this way, the end customer can treat the part as a standard component without the need for special processing or specialized attach equipment. It goes right down on the customer's board, and voila, you have a high frequency 20 gigahertz high performing filter that is at least 10 times smaller than and 10 times lighter than an equivalent waveguide or cavity filter. Filtering can often be used to combine different RF bands, which will optimize cabling or antenna performance in different systems. In this case, you can use a transmit bandpass filter and a receive bandpass filter. You tie them together at one end, connect the other end of the transmit filter to your transmitter, the other end of the receive filter to your receiver, and it's a nice way to combine two channels onto a single cable to a single antenna system. Now you might be tempted to use a power combiner splitter technology to do this, but the problem with that technology is that the combiners really only combine multiple signals together with minimal loss if the inputs are all at the same frequency and in phase with each other. And in a typical communication system, that's obviously not the case. If the signal in a splitter if the signals at a splitter are not at the same phase and frequency, any phase or frequency mismatches are going to be dissipated as loss inside the combiner. You really obviously don't want that when you're trying to maximize every bit of power out of your transmitter or every bit of signal to noise ratio going into your receiver. So filters are a really nice way to combine things with minimal loss. When you combine things using diplexers, triplexers, and multiplexers, the only loss you're going to see is the loss actually through the individual filter itself. Now you might be tempted to purchase a transmit filter and a receive filter and then combine them together at one end yourself, but that's really not the way to go, because usually you have insertion loss, rejection, and return loss mismatches because the two filter bands can adversely affect each other. So the way to do it is to order it right from the manufacturer the way you want it, diplexed, triplexed, multiplexed, and that way the filter manufacturer can modify the front ends of his filters to combine them so that you don't have those kinds of issues and you get really good performance through the system. Now this is an example of a ceramic resonator, coaxial resonator duplexer, where you have a receive band and a transmit band, and they're combined out a single antenna port. This filter, on the other hand, is actually a multiplexer. That was a diplexer. This is a multiplexer. This is a cellular band multiplexer. These two ports are 700 and 800 megahertz transmit and receive cellular band ports. These two are upper 800 and 900 megahertz receive and transmit ports for cellular, and these two are 1700 and 1800 megahertz ports. So the customer can connect 3 transmitters to this, 3 receivers to this, and his antenna at the common port, and everything's combined together for him in one shot, and it's actually very advantageous. It saves on cabling, it saves on a lot of other system components when you're trying to put a system together like that. And you have a lot of different frequency bands. So thanks for watching, and if you need any more information, please contact us at Corey Micronics. Our webpage is www.cormic.com. Thanks.